Hello everyone. I'm going to make an electrolysis video today, given how hotly it's been requested. It's definitely not one of the easier topics in Year 12 chemistry, and it can be a little bit difficult just because we've covered galvanic cells at the same time, and it's kind of a little bit hard to draw the line between, oh, well, how do we identify which one we have, and what's the difference between them? So I thought I'll go over the theory today, and then I'll put out another video in a couple of days going over Faraday's laws. So the one today won't really have much in the way of calculations. It's mostly going to be looking mostly at the qualitative type stuff, and then we'll have one looking at the quantitative aspect later on. All right, let's have a look at some electrolysis theory. So first things first, we need to be able to compare it to an electrolytic cell to a galvanic cell. So these are the main differences here. Obviously, there's going to be a bunch of similarities. In both of them, we have some kind of solution. We've got an anode and a cathode. We've got some external thing, with that be a power source or a load or something like that. Both of them we call cells. Both of them are involved in an electrochemical reaction. Couple differences here. Now, the number one that is back to front is that the anode and cathode are the opposite charges. So with a galvanic cell, you remember anode is negative, cathode is positive. Electrolytic cell, we are going to swap the charges across. Don't try and keep swapping lots of things in your head. If you just know that the charges are the only thing that's swapped over, then everything else about the definitions of anode and cathode will stay the same. So the next difference is that whereas a reaction in a galvanic cell is spontaneous, so you set up a galvanic cell and it'll just start going, like it'll just start reacting. Electrolytic cells will only work if you specifically put a voltage across them. Sometimes you might say put a potential difference across them. Basically, it just means that you plug into some kind of power source, and then it'll start running. So galvanic cells are spontaneous because they happen by themselves. They'd be pretty useless if you need to put electricity in them to get electricity out. Electrolytic cells are going to be non-spontaneous because we need to put electricity into them. And coming from that, that means that galvanic cells, you generally plug it into something that's needing electricity, whereas an electrolytic cell, you plug it into something that has electricity, that's providing the energy there. Couple more points here. Both types of cell are going to have anode and cathode have the same definition. Anode always has oxidation at it. Cathode always has reduction at it. As I said before, the thing that changes is the charges get swapped. Anode is still oxidation, even though it is now a positive electrode in an electrolytic cell. Cathode is still reduction, even though it is now a negative electrode, the negative electrode in an electrolytic cell. And because of that, the electron flow always has to go from the oxidation reaction to the reduction reaction. That makes sense, right? So the electron flow is going to continue to be from the anode to the cathode. And to complete that circuit, we're still going to need something in the middle. Now, electrolytic cells, you might have noticed, the electrolytic one here is in a single beaker here. You can do it in two. Often you'll just do it in one because it's a bit simpler, and this is a better setup for electroplating. But basically, there needs to be some way to complete the circuit. In a galvanic cell, there's more of a risk of the reactions coming together and the products coming together and reacting. So that's why they tend to be in two separate beakers. You'd have to look at what you specifically are going to get out of the reaction to see what's going to happen there. All right. So in both types of cells, we're always going to get the thing that's on the top left reacting with the thing that's on the bottom right on the electrochemical series. So if we have some chlorine gas hanging out with some silver, the chlorine gas will react with the silver. Now, the relative position of those is what's going to decide whether you have a galvanic or electrolytic cell here. So the higher up one is always going to react in any cell. If you had chlorine gas and bromine gas, the chlorine gas is always going to react first, because we get the higher reduction potential the higher we are. Regardless of whether it's galvanic or electrolytic, the higher the voltage, the more favorable the reaction is. It's just if the total voltage is positive, it'll be galvanic. If the total is negative, it's electrolytic. And if it's negative, that's why we need to add extra volts into it. So the one at the highest on the left will always react with the lowest on the right. The difference is in a galvanic cell that the top left one will always be above the bottom right one. So if we had chlorine and silver, top left is above bottom right, so therefore it's galvanic. If we had chlorine placed with some gold, the top left is below the bottom right, so therefore the chlorine would only react with gold if it was an electrolytic reaction. Now this might be when we look at all the species, I'll talk about this in a minute, it can be a little bit, you do need to be looking at the reactants in each half cell by itself, or where they're actually located, because with the electrolytic cell, it's the power source is going to force one thing to be the anode and the other to be the cathode, whereas galvanic cells just kind of pick themselves. Like the thing that has the that is the better reductant will tend to be the anode, whereas it's because the electricity can go through the circuit either way. Whereas with an electrolytic cell, because the power supply is already going in a direction, it's going to force the reaction to go in that direction. All right, so electron flow is always going to go based on the chemicals that you've got there. So this is what I was saying before. With a galvanic cell, we can always determine which direction the electrons are going to flow by looking at our electrochemical series. The one on the left will be higher than the top left. We find top left and bottom right, looking at our chlorine and our silver, for example, before. Okay, the one on the right is going to be oxidized to silver, so therefore the electrons must be coming out of it. The chlorine here is being reduced, so therefore the electrons have to be going into it. So the electrons will be going from the silver to the chlorine electrode, or the electrode where there is chlorine. So the galvanic cell, you have to figure out which direction the electrons are flowing in. The electrolytic cell, you just basically plug it in. You can pick which direction you want the electrons to be going in, and you'll probably get different reactions based on which way you plug it in, unless it's a symmetrical cell. So you might see an example of this, but basically you can have reactions that might normally be spontaneous. So example, as I said before, might have your chlorine gas and your silver. They might be there hanging out. And so you'd expect that to react and have the electrons going in a certain direction. But if, for example, you had the power source plugged in so that you had a silver plus and silver metal half cell, if you had the power source pointing so that the electrons flowed into this one, it would force the silver to be reduced, and you would get this being a reduction reaction, because the power source is what decides which way the electrons flow. So you can get some different, you can force spontaneous reactions to not occur. So we'd be stopping this chlorine and silver reaction from happening, and we might actually force a chloride ion if it was molten, because there's no water. Water would normally react. We would force the chloride and the silver to react by pointing it in that direction. If we swap the direction, then the silver and the chlorine would just react instead. And this is used sometimes on boats and things like that. If you want to protect some metal that's sitting in the ocean, often you'll basically have a really small current go into just a block of metal on something, and it'll force that to be reduced. You'll force your boat to be reduced, or things around the boat to be reduced onto it, rather than it to be oxidized and therefore rust and dissolve. So you can stop the process of rusting by putting a small current into it. All right. So in terms of electrolysis, when we want to predict a reaction, we'll come back to this when we have when we're looking at our VCAR questions. First step is we need to determine the electron flow. Remember, this is the opposite way around to galvanic cells. Galvanic cells, we need to figure out the reaction. That's going to tell us the direction of electron flow. Electrolytic cells, we need to figure out the direction of electron flow, and that's going to tell us what's the anode and cathode. So you should immediately be able to tell from the power source, unless for some reason you're not told what the power source is. Normally you just plug it in yourself, so you know what it is. It'll tell you the direction of electron flow from that. Therefore, you should know what's the anode and cathode, because electrons always flow from anode to the cathode. And then you should also be able to tell, well, the cathode is going to be negative, the anode is going to be positive. So you can already get all that information without figuring out anything about the reactions themselves. Because we've got anode and cathode, we know that anode is going to be an oxidation. We know cathode is going to be reduction, as always. And we're going to basically do the kind of standard, what equation do we have here? Have a look at what species are there at the anode. We're going to look at what oxidation reactions are there. So we'd have a look. So if we've got some silver metal, some copper metal, and some lead metal, for example, we're basically there's three different things that could happen. Silver could be oxidized, copper could be oxidized, or lead could be oxidized. So there are oxidation reactions. Which one will occur? It's always going to be the one that has the lowest voltage here. So the lowest one down on the electrochemical series, or bottom right if you want to think about it that way. So if we had those three, we had an alloy of lead, silver, and copper for some reason, and we needed to figure out which one would react. The lead would be the first to react. Now over time, all the lead would react, and once it's all gone, then the copper would react, and once that's all gone, the silver would react. So say our lead is going to react there, and then we basically just repeat that on the other side. So if it's if the other side is a graphite electrode or something, and you've got some nickel, some cobalt, and some cadmium in solution, then we go, okay, which one's going to react? Well, it's going to be the highest one on the left, remember? So the highest voltage for reduction, lowest voltage for oxidation, just because oxidation we're going right to left, so we take the negative of that value. So out of nickel, cobalt, and cadmium, nickel will have the highest reduction potential, i.e. the highest voltage here. So therefore that will react. And our overall equation here would be nickel 2+ and lead reacting to make lead 2+ and nickel. Now, one thing I didn't do here is that when we do this, again, you'll see this in a little bit, make sure to have a look at everything you've got here. Always include water when you're looking at an electrochemical series. In this case here, it doesn't really matter. It's basically going to matter if there's something that is more, that water is going to react more than. So water is more reactive than manganese, for example. On the other hand, we had lead, copper, and silver, and our water's up here, so that doesn't really matter. So make sure to check all the species you've got there, and then the highest on the left, as usual, will react with the bottom on the right. Now, make sure that you're not sitting there. So for example, if you've got two things and we've got lead 2+ and we've got copper 2+ and we've got silver, if it was separated for some reason, if you chuck them all on and they're not actually there, so for example, if for some reason you had two separate cells, again, not super common for electrolytic cells, but let's just imagine that. We can't go, oh, right, the silver ions will react there, because the silver ions aren't actually there at the anode, right? So, sorry, the silver ions aren't actually there at the cathode, so they can't react. They might be in one of the beakers, but we do need to split up what's in at the anode one and what's at the cathode one. And this can have some things to do with different questions you might see. You can physically separate where the actual chemical is to stop it from reacting. All right. And we're going to balance at the end, make sure that your electrons cancel out. Now, one thing I'd like to mention as well, it pops up occasionally. So the electrochemical series here, you'll see it's the standard electrode potential. So that is specifically at 25 degrees Celsius, and it's specifically when all of the chemicals here have a concentration of 1 molar, so 1 mole per liter. If the concentration is higher, the voltage tends to go up. If the concentration is lower, the voltage tends to go down. Sorry, I should say that basically the voltage will change. You don't really need to know too much about this. There's going to be one specific case that you kind of need to know it. But basically, if you're not at 25 degrees Celsius and the concentration is not 1 molar, the electrode potential will change. So you can use the Nernst equation to figure this out, but you don't need that for this year. Basically, we can change those voltages around. So, and the main time that this is going to show up is that if you have a sodium chloride solution, as you increase the concentration of the sodium chloride solution, so increasing the concentration of the chloride here, it will bring the voltage down to closer to this value here. As the chloride, when the voltage is pretty close to the water, you might get both reactions happening at the same time. And therefore you'll get the production of chlorine because you have this chloride being oxidized to chlorine gas. So that's one way that you can make chlorine gas. Obviously, the water will normally react most of the time. So either you have to get rid of the water, i.e. do electrolyze molten sodium chloride, which is 800 degrees or so and is kind of hard, or you do a really concentrated sodium chloride solution. So even though you're oxidizing the water, you're also oxidizing some chloride. So if they're talking about a brine, so a really concentrated sodium chloride solution, that's probably what they're doing. So it's normally like 4+ molar. So 4 mole per liter, 6 mole per liter, something like that. When you're looking at what voltage is needed to run a cell, remember a galvanic cell produces a voltage. An electrolytic cell will require a voltage because the voltage of an electrolytic cell will always be negative. So if we were reacting, what did we say before? If we were reacting nickel with our lead, I'm going to circle that, got our lead, our nickel, we're going to take the top value and subtract the bottom value from it. So, oh, sorry, other way around. We're always going to take the one that's on the left. So negative 0.25. And we're going to subtract the top one. Or subtract the one on the right. So if you want one overall rule for electrolytic and galvanic cells, it's always whichever one is on the left, i.e. the reduction reaction, and you're going to subtract whichever one is on the right, so the oxidation reaction. If this was sulfur being reduced, for example, we do 0.14 minus negative 0.13. This case, we're going to do nickel negative 0.25 minus negative 0.13. So obviously that's going to turn to a positive, and we're going to end up with negative 0.12 volts. All right, so we've got a negative voltage, so we know it's an electrolytic cell. And the voltage needed is always going to be the positive version of this, so the absolute value. And one thing that you need to put in, because it made everyone lose a mark, or made like 90% of students lose a mark last year, is you need to put a greater than sign at the start here. So if you put in 0.12 volts, if you imagine like tug of war, it wants to go in one direction. Basically, there's 0.12 volts stopping it from going. If you put 0.12 volts in, you'll basically just make it 0. If the voltage is 0 for a system, it's just not going to go anywhere. Like, why do the electrons want to go anywhere if it's 0 volts? The voltage is what means the electrons have energy, so they go around the circuit. If the electrons have 0 joules of energy per coulomb, so literally no energy, they're not going to go anywhere because they don't have an energy to go anywhere. So they need to have at least a tiny bit of energy for the reaction to start. So that's why this greater than, because if you even just have 0.12001 volts, then it'll start going. It'll be a really small current, but it'll start going. So greater than there. It'll always be the one on the left minus the one on the right. Just as an extra comment, I might make a video on this at some stage. Basically, a secondary cell is basically both a galvanic and an electrolytic cell. It just depends on what's plugged into. So a secondary cell runs as a galvanic cell. So the battery in your phone being the example we often quote, or we often use, it runs as a galvanic cell most of the time as your phone's operating. Your phone needs electricity, so the cell provides that electricity. When you plug it in, it will reverse the reaction and therefore recharge the phone. So as it's running as a galvanic cell, it turns all of its reactants into products. Once the concentration of reactants is too low, the voltage is too low for the phone to run, it'll turn off. You plug it into the wall, all of the products from the reaction will, the reverse reaction will happen, that all the products will be turned back into reactants, and therefore it'll be ready to go again later. So that's an electrolytic cell when it's recharging. Often this shows up in questions as they'll say, what is the discharging reaction, or what is the recharging reaction? All that means is that discharging just means it's operating as a galvanic cell. Recharging means it's operating as an electrolytic cell. So the reactions will always just, if you know the overall reaction for one, you can just flip it around to find the other one. Or if you know either of the half reaction, the half equations, just flip it around, you'll find the other one. For it to be able to be reversed, the products need to stay at the electrodes. Obviously, if the products aren't at the electrodes, if they've left because they're a gas or they've kind of just gone off into solution, you can't have the back reaction because there are no reactants there, i.e. the products from the original reaction are not hanging around. So if they're not at the electrode, they're not touching it, the reaction can't occur, so you can't recharge it, which is why alkaline batteries and things like that can't be recharged, because the products have gone off and they've nicked off somewhere, they can't be used there. Another thing, when you actually do have a rechargeable reaction, so that the products will generally stay at the electrodes that they're formed at, this isn't 100% unable to be affected by anything else. As a cell is recharged over time, with basically any reaction, you'll get side reactions. You don't need to know the details of these, but basically there are other random reactions that happen, and they will produce products other than those that are able to be recharged. So if they make some other random product, then they'll just float around a solution. They might even stay at the electrode, but they're unable to go backwards because they're not one of the products that normally gets reacted backwards. You can imagine it's turned into some other random chemical, like an iron oxide or an oxide or something like that. The oxide can't be reduced / oxidized back to the original iron or nickel or whatever. So therefore, you can't get the original one back. So the voltage will go down over time. And that's the number of side reactions. As we know, rate is increased by increasing the temperature. It'll tend to increase the rate of side reactions. It also means that there's more energy available, so more it'll push towards any endothermic reactions that are going to happen there, and it'll also give enough activation energy for some of those side reactions to happen more often potentially. So in terms of temperature, most batteries are designed to work around room temperature. If the temperature is too low, then the voltage isn't as high because the rate's slower. And if the temperature is too high, the lifetime of the battery, so how many times you can charge it and discharge it, this should say discharge, is going to be reduced because it's going to increase the amount of side reactions. That drop in voltage over time will go faster. That's the theory. That's all the theory I wanted to cover today. Let's have a look at some examples of this. So we've got one here. The electrolysis of carbon dioxide gas is a way to make ethanol. Okay. We've got a carbon dioxide water electrolysis cell. Electrolyte used is going to be sodium bicarbonate. All right. So we've got a graphite electrode. We've got some carbon dioxide coming in here, copper, zinc, alloy over here. This is aqueous, so this is not molten. So we do need to be aware that water might be a reactant in this reaction here. And they're actually nice enough to give us some equations here. Now identify the copper zinc electrode as either the anode or the cathode. All right, let's have a look at that. Here we've got a power source. Remember, what decides what's the anode and cathode is the basically which end of the power source it's plugged into. Positive is always going to be plugged into a negative. So positive here is going to be negative here. Negative here is going to be positive here. So therefore, if this is positive, we know this is the anode over here. And this is going to be the cathode over here. Okay. Determine the applied voltage required for the electrolysis cell to operate. So again, we're going to look at what is going to be reacting here. So over here at the copper zinc electrode, we've got some carbon dioxide coming in on one side. So we've got that coming in here. We've already been told that there's no other reactions. So we're going to have the carbon dioxide reacting. And what do we have at the other end? If the carbon dioxide is being reduced, which is a pretty logical assumption, given that it's a carbon dioxide cell, why else would you be bubbling carbon dioxide into it? We know that the hydroxide on the other side will be being oxidized. Again, we're going to take the one on the left. So this one, we're going to subtract the one on the right. So we're going to end up with negative 0.33 minus positive 0.4 equals negative 0.73 volts. Now remember that we're going to take the positive one. So it's going to be voltage needed equals 0.73, but we have to write greater than at the front. This is the question from last year that everyone got wrong. I think it had an 8% rate of people who got this 1 mark. You need to put this greater than sign at the front to make sure that you get the mark there. So we need at least 0.73 volts. One thing to note in terms of calculating the voltage here, you don't need to factor in the number of electrons here. This is not like volts per mole of reaction happened or something like that. Voltage is how much energy, it's basically a measure of how much energy each electron has. Really, it's energy per coulomb, but when we're not like mathematically figuring out what a volt is, you can say it's a measure of how much per electron or per group of electrons. So it doesn't matter how many electrons here, because if this produces 1 mole of electrons, let's say this reaction produces 1 coulomb of electrons, that coulomb will have 0.4 joules. If it produces 2 coulombs of electrons, each one will still have 0.4 joules. If it has 20 coulombs, then this will have, each one will still have 0.4 joules. The voltage just means that the amount of energy each electron has is always going to be the same, so it doesn't exactly matter how many electrons you have, because the amount per electron is always going to be the same. So that's the explanation. In terms of what that means, just don't bother. But you never need to like multiply or divide the voltage here. You can always just add or subtract them to get to the other end. All right, a balanced equation for the overall electrolysis reaction, however, is going to need us to factor in the number of electrons. So our top one here, we're turning hydroxide into oxygen and water. And we've got 4 electrons here. Now our other reaction has 12. The easiest way to go from to make them have the same one, have the same amount of electrons, well, I can multiply 4 by 3. That should work. So I'll multiply everything 3 by 3. So I get 12 hydroxides will make 3 waters, 3 oxygens, 6 waters, and 12 electrons. And the other one will just be 2CO2 plus 9H2O plus 12E negative goes to ethanol molecule and hydroxides. When you do this, the electrolyte should normally balance out. So our hydroxides have balanced out here. Our electrons should also balance out. So when we add them together, if I cancel out the hydroxides, because there's 12 on each side, so they haven't really, but the overall, we've regenerated the same amount that we used up, so there's no point putting it in the reaction. We get carbon dioxide here. We have 9 waters, and it's going to 3 oxygens plus 6 waters plus ethanol molecule, which is what we actually want. Now we've ended up with water on both sides as well, so I'll cancel out 6 of those waters, and we end up with 2 carbon dioxides plus 3 waters makes 3 oxygens and an ethanol molecule. I'm going to just double check the balance in here. I've got 2 carbons, that looks good. I've got 4 plus 3 is 7 oxygens, goes to 6 plus 1, which is 7 oxygens, that's good. I've got 6 hydrogens here, I've got 6 hydrogens here. This looks like a good overall electrolysis reaction. I should also put my states on. If you're doing balancing or something, you don't really need to write the states in the middle of your equation, because especially given this is 1 mark, the examiner is only going to look at your final answer anyway. But there we go. Got some nice states on there. Right, identify the oxidizing agent in the electrolysis reaction. Give your reasoning using oxidation numbers. All right, so the oxidizing reagent is the oxidant, is the way I normally call it. Oxidant is the thing that is reduced. So what's been reduced here? Well, the thing that's on the left side, in this case here, it's going to have to be that carbon dioxide, isn't it? I'm just going to write on here. So we've got 2CO2 plus 9H2O, C2H5OH plus 12OH. Should be able to go through and assign oxidation numbers. The carbon here is +4, oxygen's -2, hydrogen's +1, oxygen's -2. Carbon here is going to be, let's think about that. It's going to be 2x plus the carbon, +6 for the hydrogens, -2 for the oxygens is equal to 0. So therefore, 2x plus 4 equals 0. And therefore, so 2x equals -4. And x is going to equal -2. So our ethanol is -2 plus 1. Oxygen is -2 as per usual. Oxygen is -2 plus 4. Carbon's normally the thing that changes oxidation number in this. You probably you don't need to write out all of them. I'm just demonstrating that there is nothing else that changes. So oxygen stays the same. So all of the oxygens are -2, so they don't really do anything. Hydrogen is always +1, so I'll get rid of that. There we go. Carbon, however, changes from +4 to -2, so it's reduced. Therefore, because it's reduced, it is the oxidizing agent because it's gone down from 4 to -2. Goes down in oxidation number, it's reduced. Goes up in oxidation number, it's oxidized. If we looked at this, we would see that the oxygen goes from 0 to -2, so it's reduced in turn, which makes it, sorry. I was about to confuse myself there. Remember, this one is going in this direction. So we've gone from -2 to 0. So therefore, it's increased in oxidation level. It's increased in oxidation number, which means it's been oxidized, which means it is the reducing agent. So, and we would say, you don't say carbon, don't normally say carbon is the oxidizing agent. We would say that carbon dioxide is the oxidizing agent here. All right, That's a big old short answer question there. Let's have a go to multiple choice. Which one of the following pairs of statements is correct for both electrolysis cells and galvanic cells? Let's just have a look at the electrolysis ones for now and see if we can eliminate some incorrect answers. Both electrodes are always inert. That's just kind of flat out wrong. You can have a metal electrode that reacts. Electrical energy is converted to chemical energy. That sounds pretty good. We're getting the energy from the power source and we're making higher energy, so less stable chemicals that will then might be able to do stuff later. Chemical energy is converted to electrical energy. No, that's a galvanic cell. The products are dependent on the half cell components. That kind of makes sense. Like the chemicals that are there determine what products you get out at the end. I don't know why this wouldn't make sense. So that's fine right now. I'm just going to go through these even though we know that A and C are wrong. Both electrodes are always made out of metal. That's also wrong. Obviously, you can get a graphite one. The voltage of the cell is independent of the electrolyte concentration. The electrolyte concentration shouldn't matter for a galvanic cell normally. Not quite sure which one they're referring to there. That one's not right. Chemical energy is converted to electrical energy there. Basically, the concentration of the salt bridge doesn't matter. The products are dependent on the half cell components. Yes, that's what we said before. So B is not correct. D is correct here. Voltage of the cell. Oh, I think I read that as dependent, and I was like, that actually sounds kind of correct. Yeah, the concentration of the electrolytes, so the things in the aqueous parts here, is going to change the voltage, as we said before. If you change the concentration of a reactant, then it will change the voltage. So therefore, the voltage of the cell is not independent. So it's not dependent. So it's dependent on the electrolyte concentration. There you go. That makes sense? A molten mixture of equal parts aluminium fluoride and sodium chloride undergoes electrolysis. Which one of the following statements about this reaction is correct? All right, so we have keyword, you see molten or you see aqueous. That is a critical piece of information for an electrolytic cell. Well, it's kind of critical for anything, but it's particularly critical for electrolytic. You see molten, you circle that. It means there is no water. You don't need to worry about water, which is nice. So what do we have? Well, we've got aluminium ions, we've got sodium ions, we've got fluoride ions, we've got chloride ions. Okay, let's go and label them on our electrochemical series, aluminium and sodium. Let's go find them. Okay, aluminium's here, sodium's down here. Oh, we're going to have to zoom out. There we go. All right. We've got aluminium, we've got sodium, and we've got fluorine, and we've got, oops. Oh, yes, okay. Confused myself there. We have fluoride, and we have chloride, and we have sodium ions, and we have aluminium ions. Okay, it's going to make a lot more sense. All right, and I'm pretty sure the question is just saying what's going to be produced. Yep. All right, so obviously the metals here have to be reduced, right? They can only go from left to right. There's no way that they can be oxidized because there's no aluminium or sodium metal there to be oxidized in the first place. So they're going to be reduced, and therefore, if they're going to be reduced, it must be at the cathode. And the non-metal ions over here, the anions, must be being oxidized, so therefore they must be at the anode. And we know that the top one on the left will always react with the bottom one on the right. So the aluminium will be reduced preferentially over the sodium, you can say that it's because it's a stronger oxidizing agent, if you need to give an explanation, and it will react with the chloride. So therefore we'll make chloride gas or chlorine gas at the anode and aluminium metal at the cathode. Aluminium metal will be produced at the cathode, that's what we said, and chlorine gas will be produced at the anode. I think that's what I said. So C is looking pretty good here. All right, let's look at a couple more. It's nice and pink because Study Eclipse likes putting the Northern Hemisphere ones in pink. A student electrolyzed a 0.05 molar sodium chloride solution using graphite electrodes as shown in the setup below. All right, already we're electrolyzing. Have a look at the concentration. This is a very low concentration, so we're expecting quite a low voltage. If this was a high concentration, maybe we would start getting some chlorine gas or something out. At a low concentration like this, we shouldn't be expecting any funny business here. It is a solution, however. If it says solution, it is aqueous. There is going to be water around. All right, several drops of phenol red were added to the solution next to each electrode. The following observations were made as the reactions proceeded. All right, so phenol red. Okay, we're going to need to have a look in our data book. Ooh, we're getting like a crossover between topics here. Here we go. And where did I put it? That's at number 7. So phenol red. So basically, when it's acidic, it's going to be yellow. When it's basic, it's going to be red. So what I just said, acidic yellow, basic red. So I'm going to change that to a different color so we can read it. Basically, the negative, I'm also going to do that right there. It's electrolytic, so therefore the negative is going to be the cathode. And we're going to have reduction here. Positive is going to be the anode, so we're going to have oxidation here. The anode has oxidation and it's acidic. So if it's acidic, we know it's going to have a H+ product. If it's basic, it's probably going to be an OH- product. That's the most likely thing here. What color was observed at the cathode as the electrolysis proceeded? That's basically identify which of these is the cathode. So we can look across here, it's red. Writing red in blue is really throwing me off. Use the electrochemical series to predict the gas expected to be formed at each electrode. All right, so I'll leave this on here for now. So remember, we've got sodium. I'm going to write these on the side. We've got sodium, we've got chloride, and we've got water. I'll do this in red instead. So we've got sodium is way too low. There you go. We've got sodium, we've got chloride, and we've got water. All right, so if we look here, we're always going to get the top left reacting with the bottom right. So water is going to react and water is going to react. So the sodium chloride is basically just going to act as an electrolyte here without reacting itself. The chloride will not be oxidized because the water is going to be a stronger reductant. The sodium will not react because the water is a stronger oxidant. So when we get reduction, which is the cathode will have hydrogen. Hydrogen produced, and it's also going to make OH, which makes sense with our thing over here. And we're going to get oxygen gas being produced over here. And that lines up with our H+ product. So you didn't need to align the colors that I've put here, but we've double checked our work in here and it's made sense. Oops, I erased way more than I thought it would. All right, so we answered those. Imagine we wrote them in the book rather than on our thing. All right, here we go. So we're kind of done with the aqueous one. Molten sodium chloride can be electrolyzed commercially. The melting point of sodium chloride is really high. Well, it's not that too high for an ionic compound, but it's high compared to, everyday temperatures. Write the overall equation for this electrolysis. Okay, if it's molten and it's one thing, there's basically only two chemicals there. We have a look over here. We've got some sodium ions and we've got some chloride ions. There's only two things there. Therefore, the sodium and the chloride will react. So we just need to write these two equations there. So our two half equations are going to be sodium plus an electron makes sodium, fair enough. And we're going to have chloride makes chlorine gas and 2 electrons. Now, we do need to balance the electrons when we're doing our overall equation. So I'm going to multiply this one through by 2. And therefore, our overall reaction will be 2 chlorides plus 2 sodiums makes 1 chloride molecule and 2 sodium atoms there. And I'll be a good boy and I will put in my states here. Do you remember that this is molten? It's not aqueous, so therefore our state is going to be liquid. The sodium metal would also be a liquid. In this case here, I'm pretty sure they wouldn't mark you on not knowing the melting point of sodium, but alkali metals are pretty soft, so they're not low temperatures. All right, give 2 reasons why it would be difficult to carry out this electrolysis in a school laboratory. There are quite a few things you can say here. Number 1, melting point is 800 degrees. So no way to get to 800 degrees is a fair enough statement there. If we have a look at this here, making sodium metal reacts with air, reacts with water that's in the air. So you could say no way to, it might be that you can't separate the sodium metal out of the kind of molten metal. You might also be unable to store the sodium metal as well. And so this is looking at the products. We're looking at problems with sodium. Problem with chlorine gas. No way to store seal gas. That might be a thing. And no way to carry out safely given that we've got chlorine gas around. So normally you do that in a fume hood. Chlorine gas is pretty dangerous. So saying a well-ventilated area is, it would help, but it's still not good. If you're releasing carbon dioxide or something like that, that would be really bad in like a closed environment where, like, if you burnt a lot of stuff, you could get rid of all your oxygen and just turn it to carbon dioxide, and that would be not good for your breathing. But it's okay if the window's open because you can recycle the air inside the classroom with those outside the classroom. Chlorine gas is going to be bad regardless, so you do it in a fume hood or in a specially made apparatus. It does say why it would be difficult to carry out the electrolysis in a school lab. Some other considerations I would have if I was going to do this as a demo would be it's really expensive to get to 800 degrees, so these are things that I don't think specifically answer this question because it says why is it difficult, not why should you not do it. You could say it's expensive because of the temperature, and what was the other thing I was thinking of? It would be dangerous to be at 800 degrees. I don't think they make it necessarily difficult. You could say it might melt some stuff, but yeah, I don't think they're specifically answering this question here. All right, a couple more to go through. Which one of the following produces heat energy as its main energy output? This one's more of a galvanic cells question, but I just wanted to throw it in case you're like, whoa, what's this thing? So if we have a look at it, when are we going to have heat energy as the main energy output? I think we're ignoring the fact that there's no load in here, like there's nothing plugged into here. So maybe you could argue that it's short circuiting, but I'm pretty sure that's and would release all the electrical energy as heat. But I think that's not what they're arguing here. If we look through all these in turn, we've got some copper and we've got some iron. I believe that's copper 2 and iron 2. So we've got copper here and we've got iron here. Okay, so that would be a galvanic cell and it would produce electrical energy. If you've got cobalt and lead, cobalt 2+, lead 2+, we've got, where is it? Cobalt is here, lead is here. So the lead 2+ and the cobalt would react and it would release electrical energy because it's a galvanic cell again. Have a look over here. We've got nickel and we've got zinc 2+. So we've got nickel here and zinc 2+. In this case, there would be no reaction. This would need to be an electrolytic setup as an electrolytic cell, and you would need to have a current applied across it. When there's no external power source, this reaction won't happen. So B will be nothing happens. Aluminium metal and iron 2+. Aluminium is here, iron 2+. So we've got top left, bottom right. The one on the left is above the one on the right. That means a reaction will happen. When the two reactants are not separated into these half cells, and this is why we do this, so instead of just dunking the metals in there, there's nothing for the electrons to actually flow through, so they'll just react at the surface of the aluminium metal here, and therefore you'll get heat energy out. So basically, D is the case here. You'll get heat as the main energy output when you have basically a direct reaction rather than separated into these two half cells. All right, potassium hydroxide is going to be made commercially by some electrolysis here, yada, yada, yada. It's at SLC, cool. So very nicely, they've told us that we have the anode and the cathode here already. And we've got a 4 molar KCl solution. Now, immediately you should see 4 molar. It's higher than 1 molar, so we have a concentrated solution of potassium chloride. All right, keep that in the back of your minds. Explain why potassium bromide or potassium iodide could not replace potassium chloride as the electrolyte solution using the cell above. It has a few more lines. You just have one line to do that. I cut it off. So we've got basically why are we using chloride rather than using bromide or iodide? Okay. So what do we have in the solution? Try and get everything in here. Well, we have right down the bottom, we've got potassium down here. We've got water here. We've got water here, chloride, bromide, and iodide. So in the absence of, well, if we're using potassium chloride, then this water will always react, right? Because there's not another option. So it's always going to make hydroxide here. Now, if we have chloride, then the water will be oxidized because the water is a stronger reductant. However, if we have bromine or where is it, iodide, they will be preferentially oxidized instead of the water, and therefore it's going to produce some other basically gunk that's going to be in there. So we'd end up with some solid iodine floating around in there, or we'd end up with some liquid bromine kind of going around the solution, which is not great, especially because they could then go and potentially react with stuff elsewhere. So the reason here being iodide or bromide would react preferentially instead of the water at the, so we are having an oxidation there, so it's going to be the anode. Okay. As they are stronger reductants, whereas chloride is a weaker reductant than water, so will not be preferentially oxidized. I'd say that's a pretty thorough answer. You could probably get away with writing less than that, but that covers most of the points there. So I've explained why not to use these, and I've explained why you would use that. When the power supply is turned on, the chemist observes bubbles forming at the anode. All right, we said that before. It's the water reacting here, so therefore this is going to be oxygen here. All right, so for the smell of chlorine here, this is what I said before, which is that we've got a concentrated solution of chlorine here, which means there's a higher than 1 molar concentration of chloride. So therefore, the reduction potential of chlorine, this equation here, will be close to that of the oxygen here. So the oxidation of potential of chloride will be similar to the oxidation potential of water. So they'll both occur at the same time. So concentration of chloride is higher than 1 molar, that used in the electrochemical series. Bringing the oxidation potential of chloride close to that of water, resulting in both occurring simultaneously. I'll just spell it out, the oxidation of chloride produces chlorine gas. All right. Let's finish off. Write a balanced overall equation for the write a balanced equation for the overall reaction that occurs in the electrolysis cell that is consistent with the explanation given in part A3. So this is chlorine being produced. So again, that we've done this one before, I'll just go ahead and slap it in here. Chlorine gas plus 2 electrons. And at the other end, we have the reduction of water. So it'll be water goes to hydrogen gas and hydroxide. Goes to hydrogen gas and hydroxide. We've got the same amount of electrons on either side, so we should be able to combine these together into 2Cl minus plus 2H2O makes chlorine gas and hydrogen gas and hydroxide. All right. Safety risk with this, I feel like we've kind of spelled it out over the last two. Chlorine gas is toxic. Use in a fume hood. So 1 mark would be identify a safety issue. 1 would be this one here. You could also, if you wanted to, you could say hydrogen gas is flammable, something like use in a fume hood or well-ventilated area. You potentially say use a gas mask instead of a fume hood. It's probably still not good to gas out a room. You can also say keep away from naked flames. In a commercial electrolysis cell that produces potassium hydroxide, the 2 electrodes are separated by a membrane. What is the purpose of this membrane? It would be to stop the migration of the products together to react, basically. If you have a membrane that's separating an electrolytic cell, it's because the products from both half cells could potentially diffuse towards the center and react. So reacting, getting rid of each other. So I assume it's one that can kind of keep the so the issue here was the water when it's so normally this is just water and water being electrolyzed, right? So normally you'd make hydrogen gas and the hydroxide, which is what we want. We're making potassium hydroxide. And then at the other side, you've got the water and it's been oxidized to make H+. Now, obviously, if the H+ and the OH touch each other, then they'll just react and just form neutral water. So, which is not what you want, because obviously the intention of it is to make potassium hydroxide, not to make water. All right, so that's it for these electrolysis questions. Let me know if you have any other questions, and I should have one on Faraday's laws up in the next couple of days. I hope you enjoyed the video, and I will see you guys then.